Hi, my name is Mark Rulo. I'm one of the mathematics consultants in the Learning Success Center at Wachusett Community College. In this video, I will explain correlation and regression. Correlation indicates that there is a relationship between two variables. For example, we might wonder if there is a relationship or correlation between the number of hours a student spends on their statistics homework and their test grade. To answer this question, we could make a graph for number of hours as the independent variable on the x-axis and test grade as the dependent variable on the y-axis. Then construct a scatter plot showing students' homework hours and test grades. As we might expect, there appears to be a trend where the more hours one spends, the higher the grade. This suggests a positive linear or straight line correlation. This different scatter plot shows a negative linear correlation, where as the x value increases, the y value tends to decrease. This scatter plot seems pretty random. There is no obvious correlation here. This scatter plot shows that there is some relationship between the two variables, but it is not linear. We will not consider non-linear correlation at this time. We can calculate a value called the correlation coefficient to indicate how well two variables are correlated. As we have seen before, we are most interested in how a population behaves. These would be values of the population parameters. For population mean, we spoke of mu. For standard deviation, we learned about sigma. For correlation, when we are talking about a population correlation coefficient, we abbreviate that by the Greek letter rho. But as it is usually impractical or impossible to measure each individual in a population, we usually just take a sample. A sample correlation coefficient is abbreviated by the lowercase letter r. A perfect negative straight line correlation would give an r value of -1, and a perfect positive straight line correlation would give an r value of +1. Data with no correlation would have an r value near 0. As they say, the real world is messy, and seldom do data end up on a straight line. But the closer you get to plus or -1, the better the correlation. There's a formula for calculating the value of r, and it looks like this. Whoa! What does all this mean? To calculate this by hand, we would first need to make columns of the x and y values of our sample data. We would sum each of these columns. We also need a column of x times y with the sum of that column. We also need a column of x squared summed together and y squared summed together. Then we can take these values and put them into our formula to get our r, and it better be between -1 and 1, or else you've made a mistake somewhere. This is much easier to do when you let your computer or calculator do the hard work. If you have Excel on your computer, enter the x and y values of your data into two separate columns. Then, in a free cell, click equals, then start typing CORREL. Double-click on that function when you see it. Here, Excel is looking for two arrays, or sets of numbers, to test. Highlight the data in the column with the x values. Then put in a comma. Then highlight the data in the column with the y values, close the parentheses, and hit enter. Nice. If you accidentally switched the X and Y columns, don't worry, you will get the exact same number. And remember, if you do not already have Excel on your computer, MWCC students can download Office 365 for free by following the link from the main screen of iConnect. If you have a TI-83 or TI-84 graphing calculator, you can also get the correlation coefficient by letting the calculator do the work. You do have to enter the data yourself. To do that, from the main screen, hit Stat, then select 1 for Edit. If you already have data in your lists, you can clear them by selecting Stat, Clear List, and then entering the list you want to clear. They have to be cleared one at a time. To select List L1, click the second button, then the number 1 on the keypad, which corresponds to the list L1, then enter. Clear L2 as well, if necessary. Enter your data values for each variable, one at a time, using a separate list for each variable. Once you have your lists, hit Stat again, arrow over to Calc, then go down to linreg, ax plus b, then enter. If you do not see a value of r in r squared, then you have to do one more step, which is to turn diagnostics on this calculator. To do that, hit second and the 0 key, arrow down to diagnostic on, and hit enter. Now go back, hit Stat, Calc, linreg, enter, and there is our R, negative 0.146, like we saw in Excel. If you have another calculator, consult its user's manual to see if and how you can enter lists of data to find the correlation coefficient, or check online. There are often videos for these kinds of questions. This linreg function on the TI-83 calculator also gives you the value of A and B for the equation y hat equals ax plus b. That is, you are given the slope and y-intercept of the best fit line, that one that goes through the data set. This is called the regression line. The regression line is the one that minimizes the sum of the squares of the residuals. A residual is the difference between each point and the regression line. We say y hat instead of y because this is not a function with points that fall on a line. It is a regression line, and it's possible that very few or none of the points on the scatter plot will actually fall on that line. Note, for straight lines, we typically will say y equals mx plus b, where m is the slope and b is the y-intercept. Don't worry that the calculator says a instead of m. Whatever number is next to the x, that's the slope. There are also formulae to calculate the slope and the y-intercept of the regression line. But just like the correlation coefficient, this can be a lengthy thing to calculate by hand. It can be done. On Excel, you can come up with the regression line a couple ways. First, you can find the slope and y-intercept separately, and then bring them together to make your best fit line. To get the slope of the regression line, click a free cell, type equals, then SLOPE, double-click when you see it. This time, highlight the Y column, enter a comma, then highlight the X column, then enter. And to get the y-intercept, click an empty cell, type equals, then INTER, It's called intercept. Double-click on it when you see it. Highlight the Y column, comma, X column, enter. And now your regression line becomes y hat equals mx plus b. Another option is to create a scatter plot with the data. Highlight the two columns this time. Click Insert on this top line. Find Charts and Scatter Plot, and click the first scatter plot. Now, if you click the plus sign here and select Trend Line, and right-click on the line and click Format, you can select to display the equation on the chart. When you get your R, you might be asked if the correlation coefficient is significant for a given level of significance, abbreviated alpha. To do this, take the absolute value of R and compare that with the value given for the given value of n and alpha from Table 11 in the back of your book. Table 11 gives critical values for Pearson correlation coefficient. And that table can also be found online, including on the LibGuide site for the Learning Success Center. Note, the use of the name Pearson in this table is not related to the company that some students have accounts with for their math classes. For example, let's say you have 20 pairs of data and find R equals negative 0.722. Let's check for significance at an alpha of 0.05. If the absolute value of R, which is positive 0.722, is above the number in the table, which is 0.444, and it is, then there is enough evidence at that level of significance to conclude there is a significant linear correlation between the variables. You can even conduct a hypothesis test for rho. We could test if there is a significant positive correlation, or test if there is a significant negative correlation between sets of data. But since we probably don't know in advance whether the slope of the regression line is positive or negative, we would normally check whether there is any significant correlation. We do that by claiming that rho does not equal 0, which means there is a significant correlation. This is our alternative hypothesis, as it does not contain a condition of equality. And H0 becomes rho equals 0, which means there is no significant correlation. Next, we need to get our critical values for this two-tailed test from the t-table. There's a t-table at the back of your book, and they can also be found online, including in the LibGuide site of the Learning Success Center. Since we are now dealing with two variables, we will use n-2 degrees of freedom. Given the number of degrees of freedom and the level of significance, locate the critical value from the table, but as this is a two-tailed test, this number indicates the positive and negative value of the number from the table. Draw your standard normal curve, put in your critical values, and shade in the rejection regions. Next, find the test statistic. The value of the test statistic, t, equals r divided by the square root of 1 minus r squared over n minus 2. When you get your test statistic, see whether or not it falls in the rejection region and interpret your decision based on the original claim. Let's say we have 12 data points and we find r equals 0.601. Let's test the significance of the correlation coefficient with a level of significance of 5%. As we have done for hypothesis tests before, we write our claim. In this case, rho does not equal 0. Since it does not contain a condition of equality, this is our alternative hypothesis. We write the complement, rho equals 0, and that is our null hypothesis. Next, we find our critical values for this two-tailed test from the t-table using n-2, or 12 minus 2, or 10 degrees of freedom, and an alpha of 0.05. This gives the critical value of 2.228. But remember, it's plus and minus 2.228 on our two-tailed test. We can draw those in on our standard normal curve and highlight the rejection regions. Next, we calculate our test statistic using the formula t equals r divided by the square root of 1 minus r squared over n minus 2, and plugging in our values, I get a value of 2.13 to 2 decimal places. This does not fall in our rejection areas, so we cannot reject H naught. Our claim was H alpha. So, in this example, we would say that at the 5% level of significance, there is not enough evidence to support our claim that there is a significant linear correlation between the two variables. Note, even in cases where there is evidence of correlation, this is not enough to say that a change in X causes a change in Y. It could be that Y causes X. It could be that a third variable, let's call it Z, is affecting X and Y. Or it could be a coincidence that a change in X corresponds to a change in Y in this sample. It typically takes a lot more effort to tease out causation in a set of variables. Let us know if there was anything in this video that could be made more clear for a future update, and let us know if there are other videos you would like to see in this series. As always, check out our website for more information about services available in our Learning Success Center, or call, email, or stop by. Good luck, and I hope to see you this semester in the Learning Success Center.